event is in exactly 2 weeks' time, when Dr. Amanda Clare will be talking on intervals and sequences, the long and short of it. Also, new members of the BCS can obtain a 20% discount if they join before the end of August this year by using the code that you can see on your screen now. As you've just heard, this evening's webinar will be recorded and it will be available in about a week or so's time on the BCS YouTube channel. During the talk, please keep your cameras and microphones turned off so that there is no distraction. So our speaker this evening is Dr. Mariana Korsoff, and she started her career as an observing assistant at the Depreken Heliophysical Observatory in Hungary, and then moved to the UK, where she had a short period as a research assistant before taking a PhD at Sheffield University. On completing the PhD, Mariana had a postdoc position at Sheffield before moving to Aberystwyth University, where over the last few years she's been working on developing a new and novel solar flare prediction method. And Mariana is going to talk to us this evening about predicting solar flares with machine learning. So welcome, Mariana.
Thank you very much. Hopefully you can see my screen. So can you hear me?
Yeah, yes, you're fine. Yes.
Okay, thank you very much.
I can see your screen.
That's great. Okay, so good evening, everyone. And also thank you for the organizer for the opportunity to give this presentation. I am glad to be here. So before I start, I would like to give a special thanks to my collaborators, because without them, the material of this presentation cannot be here. So at the beginning of the talk, I would like to talk about what is space weather, and within the space weather, why the solar flare prediction is so important. And in the rest of the talk, I would like to show how we using machine learning, especially how we use the different machine learning techniques during our research. So we could start the presentation with a question: what is space weather? What is exactly? So the term of space weather was coined not long time ago to describe the dynamic condition in the Earth's outer space environment. And the space weather disturbances are generally caused by the solar eruption, which is coming from the solar atmosphere. And this solar eruption inundates the Earth with the strong radiation and high energetic particles, and time to time a huge amount of magnetized plasma cloud can leave the solar atmosphere and travel through the solar system. And the problem is these type of events sometimes have an effect on our space-based and ground-based technology. So there are many kinds of eruptions on the sun, but from them, the solar flares and the CMEs are the most gigantic explosion. And the most intense eruption usually coming from the so-called solar active regions. This solar active region is where the magnetic fields are highly concentrated, and we can see them as a magnetic flux arcade, and on the solar surface we can see their footpoint as a sunspot, this black one. That's why we call them as a sunspot. So basically the solar flares is an intense burst of the radiation which is coming from the release of the magnetic energy which is stored in this magnetic field structure, and they are seen as a bright area on the sun, and they can last from minutes up to several hours, and they usually occur in the lower solar atmosphere, so somewhere where the magnetic fields are very strongly concentrated. However, the coronal mass ejections are a large explosion of the plasma and the magnetic field, as you can see on the video, and they are usually coming from the upper part of the solar active regions because a few magnetic field lines just broke up from the rest of the magnetic fields, and because of it, it can travel outwards from the solar atmosphere with a speed of 500 km per second up to 3000 km per second. And we usually classify these two events based on their strengths. So the flares could be categorized in 5 classes based on the X-ray flux, what the GOES satellites measures. So the A and B class flares usually count as a microflare, so they are basically nothing. The C1, the C letter is referred to the common flares, while the M is a medium class and the X1 is an extreme class. And usually the M and the X class flare could cause some problem in our modern society because the solar energetic particles can reach the Earth within 20 minutes up to a couple of hours. And the problem is they can threatening, these high energetic particles can threatening the electronics of the spacecraft and the unprotected astronomers. And also the extreme and the extreme ultraviolet light from the solar flares can ionize the Earth's ionosphere on the day side of the Earth. And this enhancement of the lower part of the day side ionosphere can block the radio signal. And that because of this, no radio communication is possible. And the CMEs, we also classify the CMEs based on their speed. And usually these fast CMEs, which can cause a bigger problem if it's colliding with the Earth's magnetic structure, because if the CME colliding with the Earth, then it can cause a disruption in the Earth's magnetic fields and set up a geomagnetic storm. And the result of the geomagnetic storm could have an additional dramatic consequences for the number of ground bases like the pipeline or electric grid system. And also the satellites can destroyed by this huge amount of magnetic field and plasma if it hits one of the satellites. And actually the CMEs, the fast CMEs, very often occurring with these large energetic flares. And this was found based on statistical analysis. And you could ask, these type of event really happened in the past, or it is just a kind of theory in the books? And the answer is yes. So basically the space weather was born as a concept to this event. So I would say the birthday of the space weather concept is 1st of September. So at that day, Richard Carrington and Richard Hanson did the routine solar observation, and what they see, they had seen a large, big flashes on the sun, so they didn't understand what is this. But basically, we call this event as a Carrington event because Carrington was the person who first reported that a strong geomagnetic storm happened 18 hours later after these big flashes. And now we understand a huge amount of CME also occurred with these big flares and rushed straight to the Earth. And a huge electric surge occurs from the ground-induced current in a telegraph wires, both in Europe and in America. And during this electric surge, who worked in a telephone company and they wear this iron headphone, some of them get a serious electric shock. And the other thing is space weather event, what we usually show. This is happened in that day in Quebec, Canada. So again, a huge CME just collided with the Earth's magnetosphere and set up a geomagnetic storm. And this interaction of the solar plasma with our ground-based facilities actually created an electric current in the facilities across from North America. And later, this current found a weakness in the electric power grid of Quebec. So basically, one of the transformer station burned down, and because of they had to repair everything, which took a couple of weeks, and because of this, many people was without electricity for a couple of weeks. Or just in our lifetime, one of the famous solar storm series, what we call Halloween solar storm. During this period, many flares occurred, large flare occurred, and also CMEs. During that period, many satellites was failed or just lost for connection, but also many of them went to a safe mode. And even one CME caused a couple of hour electricity blackout in Sweden. Or one of the most famous one from the last 10 years, basically this one, we were just lucky because that CME actually avoid the us with only 30 degrees, but the CME collided one of the solar satellite, and thanks to this collision or accident, the satellite could measure the parameter of the CME. And based on that, few researchers conclude that if the CME would collide the Earth, then it could cause a widespread power blackout almost in entire Europe. And to repair it and establish everything again, it would take a couple of years. So in this case, we were lucky, but sometimes the space weather event can cause useful things, because it is well known the SpaceX Starlink satellites are not the favorite for the nighttime astronomer, because it can cause some problem during the observation. So basically, a little bit less than a month, because of the geomagnetic storm, more than 40 satellites was just kicked out. So now we can see that basically the question is not anymore whether it will occur, but the question is when. And this is what we would like to predict somehow, but how we can do it. First of all, we have to monitor the space weather continuously. Most of the cases we are using satellite data, but also we using ground-based telescope data. So to measure the space weather event, maybe the three more important satellite mission, these are. The first one is a so-called geostationary operational environment satellite. This is a kind of satellite series, and some of them are measuring the energy of the flare, the intensity of the flare, when it happened, how long does it take, and what is the position on the sun, and etc. And the second one is the so-called solar and heliophoric observatory, the SOHO. That was a kind of groundbreaking mission because this satellite allowed to us to continually observe the sun, and we could use this measurement to study the solar events which have an effect on our modern society. So the satellite basically lasted far beyond its initial planned 2-year mission. So the scientists worked hard for an upgraded version, and the Solar Dynamic Observatory, as a siblings of the SOHO, was launched in 2010. And unfortunately, this SOHO, it's also getting old. And just last year, the new little siblings, which is much smarter, was launched, the Solar Orbiter. And just a few months ago, they started to, it is all the observation for the public. So we are still learning how we can use these of the solar orbiter data. So that's why I would say until that, we are still using these observations to develop flare prediction methods. So because we have so much amount of data, that's why we have to find some kind of tools what we can use to handle that amount of data. And one of these options is to use machine learning. In general, the machine learning has two big family. One is the so-called supervised learning machine, and the other one is an unsupervised learning machine. The unsupervised classification, also known as clustering. So the unsupervised classification applies when we want to discover similarities in the data without deciding the prior the division between the classes, or with other words, without specifying classes and their labels. This method is well suited in a case when the ground truth cannot be specified. However, with the supervised learning machine, there is two subclasses. One is the classification, and the other one is a regression. The supervised regression in principle is a task which can be successfully set and achieve good performance for any problem for which there is a physical motivated reason to interfere some time lag causality between a set of driven and the output of the interest. And in practically any regression problem for the continuous variable can be simplified for a classification problem by introducing the arbitrary threshold and dividing the range of the predictants into classes. And especially in the solar flare prediction, we are mostly using supervised classification because that the physical-based approach will never be feasible for a forecasting space weather event is essentially due to the large separation of the scale in space and time involved. So the short time lag between the causes and the effect. So in this respect, we believe that it is fair to say that the space weather community has a good understanding of why some models have a poor forecasting capabilities. For example, what is the missing physics in approximated model, and what links to the space weather prediction chain will benefit more the coupling between the data-driven approach. And interestingly, I would like to emphasize that in the space weather, we never use directly the solar observation, the full disk image, as an input data. We usually using features which are extracted from the solar images, like the active region, and also some physical parameter of the active region. Like, for example, in the middle, we can see the full disk magnetic field observation. So from that observation, we are mostly interested in that part where is this strong white and strong black patches. So basically, these are the photospheric foot point of the magnetic field arcade. The positive one, this white one, is referred when the magnetic field is outward directed from the solar interior, and the negative one is when it's directed to the solar interior. And for example, here we can see that in some cases the positive and the negative polarities are nicely separated, and this is one of the features. It means that it should be this magnetic field arcade. It should be kind of a simple one. It's a nice loop structure. Why? If we look at that one, we can see that this positive and the negative polarities are very close together, and they are also mixed. And it means that the magnetic field structure, the internal connection of the magnetic field, are very complex. And we know that if something is complex, then it could generate a big problem. So basically, in a first view, we could use the kind of classification system, what we call, well, so in the solar physics, we using Montvieson classification system, which give information about how these two polarity are close or mixed together. And based on statistical example, and also because the machine learning is a kind of statistical analysis, we could study that the simple magnetic fields usually producing a low energetic flares, while if it is getting more complex, then they are producing large flare eruptions. However, the Montvieson classification skill is a kind of nice tool to indicate which active region has a capability to produce large energetic solar eruptions in the near future. However, we need more parameters which quantifies the active regions and allow a physical comparison and a deeper understanding of the actual causes of the solar flares. And usually these parameters are scaled proportionally with the involved fundamental physical quantities, which are responsible for a flare and the CME eruptions. Recently, in our literature, we have more than 200 predictors exist. And to be honest, just few of them are capable to predict accurately the flare and the CMEs. So before it was revealed that just some of them are capable, we didn't know which predictor can be used for a different purpose. So a couple of years ago, a few scientists get a huge grant, and they collected all the flare predictor parameters which was available in the literature, and also our parameter was taken into account, and they used different machine learning techniques. And these machine learning techniques also was supervised classification. And what they found first, only just 40 parameters would shown to be a kind of good predictors, which can be useful. And also here, our parameter was named one of the best 10 parameters. And actually, it was a kind of good news. So, and these parameters call as some of the horizontal magnetic gradient. So basically, this parameter measuring the internal connection between the opposite magnetic polarity within an active region. So if this parameter, the value of this parameter is getting lower and lower, that means that the magnetic field is a more simple one. But if this parameter, the value of this parameter is getting larger and larger, it means that the internal connection of the magnetic field are more complex. So in this case, if it is getting more complex, then it has a chance to produce a large energetic solar eruptions. So their result was encouraged us, maybe we could improve the flare prediction capability of this parameter. So that's why we decided we are developing a new parameter, what we call separation parameter. With the separation parameter, it's a little bit more simple compared to this one. Basically, here we are measuring the distance between the two opposite polarity. And the meaning of this parameter, if this parameter is smaller and smaller, then it means these two opposite polarity are close, getting close to each other. However, if this parameter, the value of this parameter getting larger and larger, then it means that these two opposite polarity getting further away. So to test the joint flare prediction capability of these two parameters, we used the binary logistic regression algorithm. This algorithm is a very simple but widely used machine learning techniques. This logistic regression is one of the I would say they are using for a two-class classification. So the logistic regression is a special case of the linear regression where the target variable is discontinuous in nature. And the discontinuous means that there are only two possible classes. In our case, do we have a large energetic flares or we don't have a large energetic flares? And we choose also this logistic regression because they also calculate the probability of the occurrence of the binary event utilizing the logit function. So in this case, when we have the answer, do we have a large flare? And the answer is yes, then it's also give the accuracy of the prediction. So what we did exactly, so we analyzed more than 15 years data, and within this 15 years, we have more than 1,000 active regions. And almost every active region produced some flares, maybe just a micro flares, but sometimes a large flares. So what we did, we took into account the largest intensity flare of each active regions. So in this case, we have one flare and which is corresponding to one active region. And after we took as a reference time of the occurrence of these selected flares, and we calculated these two parameters of the active region 24 hours, 18 hours, 12 hours, and 6 hours earlier. So these are basically our prediction windows. And after that, for each issuing time interval, we randomly extracted the 2/3 of the data for a training purpose of our machine learning method, and the 1/3 of the active region went to the test data set. And in this case, we don't have an overlap between the training and the testing set. So basically, it is one of the major rules during if we are using machine learning. The training and the testing set cannot share the same data, because then the prediction could be false. I would say we could get a higher accuracy, but this is not the real one. So now we are happy because our training set and the testing set are totally independent from each other. That's why we could start to training our model. So we set up two models. The one model was based on, we just take into account the actual value of the two parameters and the largest intensity of the active region. So this was a kind of a simple model. But in the second model, we went a little bit further. We identified different threshold levels to see if we identify a well-defined threshold, this can be further improve the fair prediction capability of the parameter or not. So after when we did the training, when the machine learning techniques learned from the training set how could predict based on the information, we tested this model. And to test the performance of our model, we need to use different metrics. And especially in the space weather, we have another big problem because our samples are strongly class imbalanced, which means that we have far more negative examples than positive ones. So basically, we have much more quiet the observation than, for example, these stormy days. So it means that we have just a few large energetic flare eruption happening within these 15 years. I think we had only just 40 compared to the 1,000 active regions. So because of this, we have to use that kind of metrics which also take into account the strong class imbalances. So basically, they are weighted parameters. So the FlareCast project, what I showed before, which found our parameter is one of the best one. They said the prediction capability of this parameter is 70%. And now with these joint with this other parameter, we found that we could increase the prediction capability with a couple of percentage. Okay, we was a little bit surprised, but anyway, extra percentage is even better than the minus percentage. And based on, first of all, on the accuracy metrics, we can see that the first model performance better compared to the second model, where we set up a different threshold. But however, if we take into account these two most important metrics, then we can see that actually the second model with the well-defined threshold level more accurate compared to the first model. So this was one of the study where we used a kind of a simple approach. And now I would like to show another study, which was basically, first of all, not proposed by us, but we wanted to use, and it turned out this model has some big mistakes. So basically, just to give an impression why this model was kind of a wow model. So before 2011, we didn't have a chance to investigate the far side of the sun. We could only investigate the side which is facing to the Earth, and had a little knowledge of what happened to solar features after they are rotating out of the view. So, for example, would the active region grow larger and turn back and produce large energetic flares, or even they just decay away? Or what about the new active region, which are forming on the far side of the sun, and they can develop for a complex magnetic active region, and when they are turning into our view and facing with us, then they just produce a large flare eruption. And the problem is we cannot predict this type of event, which will be happen, which is basically just turned in and they are exposed. So, but after 2011, two satellites was launched. They are called Stereo A and B. So they are going around the sun. And with these two satellites and with the SDO satellites, so the SDO satellites just studying the sun which is facing with us, facing to us. And these two stereo has a capability to look behind the sun. So with these three satellites, we have a kind of wider view of the sun. And so based on this, sorry, just to go back. So the problem is these two satellites only just producing UV images, but for us, we need magnetogram images for a prediction as I showed before. So, but the SDO is producing UV images like the two stereo, but the SDO also producing magnetogram data. So that's how they proposed the artificial intelligence model. They could use, provide far side magnetograms based on if they are just using the EUV observation from the stereo satellites as an input data. So they use the conditional generative advisor network as a SIGAN AI techniques. But first of all, they had to teach the AI for a so-called polarity halo, which means that the sun has a 11-year solar cycle, and the sun is rotating from the left to right. And during one cycle, the leading polarity of the sun is always, of the sunspot is always positive, while the following polarity is always negative. And on the other side of the south part of the sun, the leading polarity is a negative polarity, and the following polarity is the positive one. And after 11 years, this rule is basically changed. And now on the north side is the leading polarity become the negative polarity, and the following one is the positive polarity. And on the south part, the positive one is the leading polarity, and the negative one is the following polarity. So first of all, the AI has to learn this rule, and after that, this for a training purpose, they feed the AI with the AI images and the corresponding magnetograms from the SDO. So in the EUV images, you can see the loop structure of the active region. And for example, from here, because we know that the sun is rotating from left to right, then this bright area is the magnetic loops. So from that point of view, this foot point of the EUV is corresponding to the positive polarity because of the halo, and the end of the loop is corresponding negative polarity. Or in this case, we can see that the beginning of the loop is corresponding to the negative polarity, and this one, the end of the loop, is corresponding to the positive polarity. So based on this, the AI can be trained. And after that, on the testing data set, they compare the generated AI magnetogram and the observed, the corresponding observed magnetograms. And interestingly, when they calculated the total unsigned magnetic flux on the full disk images, basically they found almost a perfect match, only just 3% differences. And this is a kind of wow category. And also in the active region cases, they found almost a perfect match. With the quiet region means that this gray area where the magnetic field is very low, but even here the correlation is very good. But in our case, basically we are interested about the active regions. So that's why we took this opportunity and we wanted to develop our flare prediction method. We wanted to see, can we use the AI generated magnetic from the far side, and if we can do it, then we wanted to test if we do a prediction. Can we predict that when the active region is turning our side and give a prediction, do we have a large flare eruption or not? So that's why we took this method, and basically we did almost the same what they did. So first of all, they took the September and October images of each year for a testing purpose, and they used the rest of the 10 months data of each year for a training purpose. And what we did, we just increased the iteration with 3 times, because more iteration have to gain more stable knowledge for the input data. As we usually say, the repetition of mother of knowledge. So because we teach the same AI a little bit more effectively, and after we started to compare their result and our result. So they proposed that the full disk image, the full disk AI generated magnetogram is almost perfect with the real observed magnetogram. But in our case, we found only just 60% match, which is still good, I would say. But when we calculated the normalized mean square error, actually our error was very high compared to them. They have almost nothing error. So, okay, we said it's fine. Let's see what's happening with the in the active region cases. And this is where their method really failed. So just to show an example, for example, the AI could only identify the half of the active region on the magnetogram observation, on the generated AI magnetogram compared to the observation. For example, here one active region on the real magnetogram, while on the AI it cannot detect it. Or, for example, here the AI identified an active region here, but in reality, on the real image, we have here this active region. Or if you look at that one, these are more tilted compared to this one. So the position is also not so good. And even in this case, the AI calculated the negative polarity here. And actually, this is a huge one. And in the observation, we don't have. So it's somehow failed in our case. And we started to think about what could be cause the problem. And we thought maybe there was a kind of potential data leakage, and they used a very low iteration compared to us. So the sun basically rotates slightly less than a month, and one active region can live for 2 weeks at minimum. So basically, they took the September and the October of each year, the September-October observational data of each year for a testing purpose, and all the rest of the observation went to the training purpose. However, if an active region was observed end of the August, and we know that an active region lives at least 2 weeks, and then it means that these active regions still can observe on a September during the September. So it means that very often the training set and the test set share the same active regions in many cases. So to test our conjecture, we built a new model. What we did, we took the October and November observation for a test set, and we left out the September and December data set. So it means that we just take into account the January, February, March, April, May, June, July, August data set for a training set, because if the active region was observed end of the August, then we cannot observe this active region in October. So basically, we left out the September data. So in this case, we don't overlap between the testing and the training set. So they are totally different. And after we applied the same method, what they proposed, and we found that with this new data set, all the performance dropped further 20%. So basically their method just failed, but thanks to this, we could write a Nature Astronomy paper as a response to show how their method is actually not accurate. So as a summary, the take-home message would be, when we would like to apply machine learning, first of all, we have to know how can we trust the algorithm that we do not have a full control of. And also in the space weather, or in other fields where we have far more negative example than positive one, we have to use different metrics, because sometimes some of the metrics can mislead us and give a false result. So thank you very much. And if you have any question, I am happy to answer it.
Thank you very much. If anybody has questions, I can either put them in the chat, or you can now unmute yourself and ask them in person.
That's a nice question. Yes, I would say yes. So the question was, so could the fast CME coronal mass ejection travel from London to Berlin in just over a second, or Sydney if the travel, yeah. So it's so this type of CME is actually not so often occurred from the sun. But the problem is when they are colliding with the Earth, then they can cause a very big problem. But yeah, so your question is yes, use for machine learning. Not the average one. You can do it on a simple desktop computer. Because as I told, for the machine learning, we are don't using the direct entire solar images. We just the some part of the image, and also we just calculating the parameters. But it takes time actually. The running time is usually a month or 2 months.
So does that mean that with these fast eruptions, that you have no hope of warning of their effects?
So the CME can, so the problem is the flares which are generating high energetic particles and radiation, they just can cause problem in the electronics of the spacecraft. The CMEs also, the CME can arrive within 1 day up to 2 days, so we could kind of prepare ourselves, but the problem is which politician could decide we need to switch off. So we could protect our facilities if we just switch off, but to switch off, the politician has to be sure to give an order for it. And now the problem is we have some uncertainties and we cannot go to the Polish, the prime minister, please switch off because we are 70% about the huge CME will come, and you know, so that's why we have to develop our method to be more accurate.
Yeah, thank you. There's a question: can the algorithms be shared?
It's already on the GitHub. So if you, I don't know which one. Both of them are on the GitHub actually in the papers. It's the link, but I am, if you contact me by email, I am happy to send a link. What undergrad and postgrad degrees did you do, please? As I'm a student who will soon choose a degree and I really want to go into an AI project in the future. So for Katrin, I did physics and maths, and basically I read a lot of things about the AI first to just get an impression, what can I do with it? And after that, I get a project and I started to develop the AI method. So what I would, these codes are basically available. For a simple one, for a classification, there is a Python package which are using machine learning, but to set up the parameters, you have to be careful how you are set up the models and everything. Actually, I would say if you have a nice project where you should use machine learning, I think you could also learn from yourself. But also, if you go to the IT, where you can learn, I don't know, some programming or etc., then you could pick it up. But I would say you also can learn from the internet. This is what I did actually, and I did it within a half a year. Sorry, can you repeat your answer again? As my Wi-Fi just crashed. That was the for where she can.
For Catherine.
So I would say for the I don't know, computer science, this is the most obvious to go there. They are teaching some AI, but I would say you also can take a course from the internet and just download the Python package and you can learn it within a half a year. Sometimes with, oh, sorry.
So you missed a question, I think. There's one from Nick saying, will new observations such as from the recent Parker Solar Probe influence future approaches to prediction?
Sure, because the solar probe producing much more better data. For example, the first one, the SOHO one, the resolution was 4 times less compared to the SDO. And now the solar probe providing a much better data. So definitely.
There's a comment from Amanda saying, sometimes with machine learning, it can be very interesting to inspect the instances where the computer decided incorrectly in order to understand what kinds of things it gets wrong and maybe work out why. Do you know why the recall was low for flare prediction?
This is based on also your data. So that's what I say at the end as a summary. You have to know your data, and in the space weather, we have to know how the applied parameter has a physical meaning, and they are really including those information which are important for a flare prediction. So as an AI, you could use the AI to work bigger data set, but you have to be conscious and also careful. What type of data do you use? What type of metrics do you use and to interpret? For example, I showed here almost 7 parameters, and based on these 7 parameters, you have to conclude correctly. So for example, as I showed here, I am still sharing my screen. No.
But yes, we can see your.
Can you see my screen?
Yes.
Yeah, okay. So for example, here I listed 7 parameters, and based on the accuracy, as I told, the first model, I would say it's much better compared to the second one. Based on the recall one, yeah, it's very low, but the main conclusion was not based on this. It should be based on all of them. And that's why I said the second model actually performed much better. So yeah, you have to take into account all the parameters and use as much as you can, because 1 parameter is not enough or 2 parameters is not enough. And
can you show some data live right now to see how the algorithm works?
No, I'm on my laptop and this is not connected, sorry. Yeah, then that's it. Mitchell. Oh yeah. Okay, thank you, Mitchell, for the link. Katrina, just.
So yeah, there's a link to.
Yeah, I think it's very nice to take some of the course, and after that, just to understand how to use machine learning and what type of machine learning can you use for your goal. Oh,
Okay.
Oasis University also have. Okay.
Are there any other questions? Oh, yeah, and Amanda has also put a link into some of the courses here in Aberystwyth. Yeah.
That's good, yeah. So you can choose, even there is online courses. So.
Okay, so it looks there are no further
it.
questions. So thank you very much for a very interesting talk, and
thank you very much for the invitation.
You're very welcome, and we look forward to seeing everybody at our future events. So thank you, everyone, and good evening.